is Naomi Cole. I have a small consulting firm called Construct in Portland, and I have the privilege of leading some of the new program design initiatives for Energy Trust new buildings, one of which is this umbrella of new offers, this suite of new offers that we're calling Future Ready Buildings. And we're super excited to be formally launching today. This work has been in the works for about a year and a half. With a team of partners who we affectionately call the Dream Team, some of whom you're going to meet today. And as Kriya mentioned, we're particularly lucky to have some of the national thought leaders around these concepts of future-ready buildings and grid interactivity based here in the Northwest. And I want to call out and give credit to the full team, which includes New Buildings Institute and PE engineers, who you'll hear from today, but also Sarah Architects and Brockman Sustainability Strategies. So we've had a team working closely with Energy Trust and the New Buildings program to spend a year really doing market research, conducting interviews, looking at program precedents around grid interactive efficiency programs. And all of that work has come together to help us define and create this sort of brand under Future Ready Buildings and develop a whole suite of offers that we are going to be rolling out over the next several years. So there's a couple that are now in the market, and part of that plan includes training and education and resources, which you will learn more about today. So without further ado, a big part of our work was defining what do we mean by future ready buildings, and you can see the definition here. It is an energy efficient building that flexibly and strategically adapts when and how it uses energy to achieve the benefits that are of interest to building owners, many of your clients, around reduced operating costs, energy savings, functionality during disruptive events, so that resilience piece, and then also reduced carbon emissions. And this piece of when and how a building uses energy is really, I think, the crux of what makes future ready buildings different, and is a lot of what you'll hear about from the team today. And I think folks are pretty familiar with energy and cost savings, increasingly resilience, and also the decarbonization benefits. But just to call out a little bit more what we mean here, I think the resilience benefits that future ready buildings really support, the way we've defined it, is the ability of a building to function during disruptive events and maintain core functionality for things like, refrigerations for emergency medication, or the thermal mass of the building allows it to actually stay cool for several hours during a peak event and allow the air conditioning to come on later. So those are some of the things that we mean when it comes to resilience and future ready buildings. And then from a decarbonization benefit standpoint, this piece about when a building uses energy significantly impacts the emissions profile of that building. And so you'll hear about that today. And this idea that a net zero building that's an island is actually not always the best thing for the grid, because it still has peak demand during periods when other buildings on the grid have high energy demand, and that's often the time when it's the most expensive and the dirtiest power that's adding emissions to the grid. Next. So why does it matter when a building uses energy, right? So as I was just talking about, this idea of shifting energy use to periods of lower demand can save money for owners and qualify buildings to participate in utility demand response programs. And it also helps buildings improve their resilience and maintain functionality during extreme weather and wildfires. Next. So what makes a building future ready? A lot of these strategies are the things that you all have been working on for decades, the sort of best practices in high performance buildings. So you can see kind of the four components here in the different colors that make up a future ready building. And I actually really like the pyramid here, especially if you're familiar with Energy Trust's Path to Net Zero program, because you want to start with the biggest bang for your buck, right? The efficiency vegetables, passive systems, good building design. This is the New Buildings program, so we have an opportunity to influence those strategies. And then you layer in the efficient active systems and technologies in the building, then renewables and storage. And then what's really different here, what goes beyond the Path to Net Zero program, is this idea of grid interactivity. And a building thinking about, again, not just being an island, being a net zero island, but being a good neighbor on the grid and being able to communicate with signals from the utility. And so you'll hear a lot more about what that looks like next. So when you look at the building and the systems, here's some of the different components that make up a future-ready building. Again, I think if you look at the blue and the orange, these are the strategies that you all are familiar with and that are part of building models. The lighter green is the piece that's really that grid interactivity. So thinking about individual appliances that have grid communication abilities, smart electrical panels, and potentially additional controls that allow for that two-way communication or allow a building to turn on or turn off certain functions. Next. So what we're excited about in the New Buildings program is that, as I mentioned, we are launching a bunch of incentives over the next few years. Some of these are already available to you in the market. You may have taken advantage of them. These incentives have actually been out for a few months now. And the first is a simple add-on to the early design assistance meeting. So if you've participated in early charrettes with your project team to talk about energy efficiency, there's an additional $500 to talk about the potential for grid responsive features on a project. And this is already part of the template agenda if you use that for other energy trust incentives. And then what you're going to hear about today are these 2 tiers of technical assistance incentives. One looking at preliminary demand analysis, which is based on this calculator that NBI has built. And then the second, which is a deeper level of analysis to go into particular system or strategy, such as modeling the financial revenue from demand response programs, or looking at battery energy storage systems and how that supports a building's resilience. So you're going to hear a lot more about that. And even in the next year, we have new offers, such as a lot of new resources coming, looking at like minimum systems capabilities for future ready buildings. What are the kind of performance thresholds that make it future ready, template language for owners' project requirements for them to build in future ready expectations into their contract agreement with their design team. And then down the line, we're exploring incentives for things like controls and other grid interactive technologies, as well as many, many other resources that you're sure to hear about in the coming years. And with that, I think, yeah, one last slide, and there will be a link in the chat for you to go to the website that has information about all of these offers. And I'm super excited to introduce Alexi and Noah and Forrest and invite them to come online and turn their cameras on. And we'll turn it over to Alexi, and we'll have about an hour, maybe a little less of their presentation, then we'll have time for Q&A. So invite you to add questions to the chat, and we will track those as they come in. All right, Alexi, thanks.
Thank you. Pleasure to be here. I am Alexi Miller. As noted, with New Buildings Institute, I'm the Director of Building Innovation at NBI, and glad to be here today. NBI, New Buildings Institute, is a 501c3 nonprofit. We've been doing equitable building decarbonization for 25 plus years, going on 30 years now, actually. And we actually are headquartered at the PAE Living Building in downtown Portland. I'm joined today by my colleague Noah Gabriel, say hello, and Forrest from PAE. PAE?
Hello, Forrest Angus at PAE. We're consulting engineers, MET, LT, and R, regenerative design. Senior associate and one of the leaders within that group, so a lot of our building analysis work. We've been in the Portland area for almost 60 years. We've got offices now up and down the West Coast, as well as on the East Coast and some places in between. Our focus is engineering that matters. So really looking at the more sustainable design approaches and meeting complex engineering challenges with the right solutions that help kind of drive all of us forward. Our living building that we actually share with NBI and others it exemplifies a lot of the things that we're going to talk to today in terms of design strategies that really look at that future readiness. It is a full living building challenge certified building. So net positive energy, net positive water, and a lot of resilience strategies incorporated throughout the design, as well as grid interactivities. We also focus a lot on the people within our company and our planet goals as a B Corp. And yeah, excited to be here and talk about some of the ways that we've leveraged analysis to help drive these things forwards, and some of the work we've been doing with the rest of this team to help develop this program.
Thank you, Forrest. Yeah, it is a really remarkable building built to last 500 years and exemplifies a lot of what we'll talk about today. If you want to come take a look, I'm sure we'd be happy to show you.
Yeah,
so what we'll be talking about today, Naomi did describe the program offer. Just gonna briefly describe that, but I won't go too deep. But it's really cool, and I'm excited that this stuff is live and on the web now. We'll cover what we mean by this. Naomi gave the proper definition, but we'll get into a little more what we're talking about. Talk about like the why, because when working with a client doing, for example, energy modeling, which is why we're all here, it's really important to start with why are we bothering with this stuff at all? What are we trying to get out of it? What are the client's drivers or the project drivers, and what are the value streams that we are hoping to see happen as a result of a great design, which is where the modeling contributes. And then the how. What are some key strategies? We're going to go end use by end use, talk about building systems, some kind of spec recommendations, and specifically modeling considerations to keep in mind. Got a couple flags for tools, and we want to keep about 20 minutes for discussion at the end. So this is a part of the New Buildings program, which covers new construction and major renovations under the Energy Trust of Oregon. And I'm so pleased that we have a website with information about this offering. There's a 101 PDF document that you can check out. There are some resources, and it gives you lots of information about things like the incentives. So this is eligible to projects in Energy Trust territory, which is Oregon, served by one of these utilities shown here. And Naomi gave a rundown on the incentive offerings, but right, you can get $500 toward a meeting with, for example, me. Come to a meeting and talk to folks, give an idea of why and what and how a little bit. And then there's that early design assistance for the charrette, and then the in-depth modeling, right? So we'll talk about what happens in the modeling, but keep in mind the incentives help cover it rather significantly, 60%. These are the details in here. This is in the on that website that I just linked. Sorry, would you stay in place there? It's on the website that I just linked. Great stuff. I'm so pleased that it's not only live, it's on a website with lots of good resources. So what are we talking about? Why are we bothering? Very brief background. For many years, we have had an electricity grid that has had big central conventional power plants deliver electricity to the grid through the transmission infrastructure, and it goes off into the distribution grid, gets stepped down, and serves offices and homes and whatever else. Then we've started to see some more distributed generation, as well as larger central resources coming online that are maybe more variable, like wind and solar, for example. So that has started to create a need for some more active grid management in a couple places, kind of here and there. We've seen interesting things pop up behind the meter as solar has gotten way cheaper, and a little bit later, but equally meteoric, energy storage has gotten way cheaper. And then, it may be way cheaper, but it doesn't mean it's the cheapest option. So then we get like the smart stuff in behind the meter and starting to think about the design elements, the passive strategies that help us get this decentralized, highly reliable and more affordable, much cleaner energy system that we're working toward. So this is kind of within the context of the transition on the grid some of that's like big behind the meter grid stuff. You're like, yeah, my client doesn't really care about what happens on the power plant. They want the power to come on when they flip the switch. But this is the context in which we're existing, and it's changing. So it's driving us to start thinking about some of these trends. Forrest, you want to give us a little rundown on some of these key trends?
Yeah. So, when we've had discussions with a lot of our clients around, what are the transitions that are driving the discussion? One of the most common things is the prioritization of resilience, and trying to get to an understanding of what does resilience mean for each building owner or operator, and how can we incorporate the strategies that help support that, while also communicating how those same strategies can help make the larger community more resilient by helping support the grid efforts. And so making those connections to the utility partners and showing ways that those interactions can happen, focusing on what the interactions actually impact overall, and understand how the shape of the utilities rate structures is changing over time. We're going to start seeing potentially more rate structures similar to California. And the value of these type of strategies can be exemplified by looking at those type of trends and the direction where we may be going, while also communicating the immediate impacts with the utility partners. And then, just the importance of understanding when and how to address these different design strategies, and make sure that we're having the conversations early and upfront so that the cost of implementation can be lowered, and we're able to plan early on for that incorporation, because some of the electrical infrastructure and the way that things are distributed is really critical in our planning efforts, and adding this stuff in late in design can be a challenging application there. And then just looking at overall, distributed energy resources, how those impact the bigger picture in terms of decarbonization, what's the right way to evaluate that, and how best to communicate that out to teams and stakeholders.
Thank you. So Naomi read the definition, but I'll just emphasize that we're thinking about passive strategies, active strategies like mechanical systems, smart grid integrated stuff, and distributed energy resources like behind the meter PV and storage, right? And we want to get some of these values at the end. We want to lower cost. We want to improve resiliency, keep things running when the power's down, for instance, and we want environmental benefits like carbon savings. So what makes a building future ready? Well, it's got some features that help make the energy use low, flat, efficient, and flexible. Sometimes what we mean, we talk about a demand profile or a load shape. That's the curve across a day or longer, often from an energy model. So a low load shape is just lower, it's less in general. The y-axis, the vertical, is energy use or demand. Flat means it's not so peaky, it's not so spiky, right? So we want these efficient systems, passive systems, day in, day out. They keep things comfortable when it's hot and really cold, summer and winter. And we want to, we start with the passive stuff. This is in order. Energy efficiency is the first fuel in the loading order, and it's also the first place we go for future readiness, as well as just in these projects in general. And then we want to make sure that our active systems, our mechanical systems, are highly efficient. HVAC, lighting, water heating, whatever that may be. And then we've got the on-site distributed energy resources, solar systems, battery storage systems, perhaps controls on EV chargers with some degree of control over when and how that energy gets used, and make sure that they're also contributing toward resiliency and carbon goals. That's not a guarantee that happens. And then, finally, we want to make sure that we're designing for flexibility, that we're able to have these automated smart communications with the utility or a third party to do things like play nice with demand response programs. The why, when I go to these early design assistance meetings or these these meetings, right? That, hey, $500 to have a meeting with the client. Sometimes I go to these. And one of the first things I ask is like, why am I here? What are you trying to get out of this? It generally boils down to one of these value streams. We want to be lower carbon, we want to be more resilient, we want to save money, or we have to. So I'm going to kind of run down like a little bit of what these value streams mean, because that's the starting point, and all the fancy modeling in the world doesn't really matter if you're barking up the wrong tree from the get-go. So this helps us make sure we're pointing in the right direction. So decarbonization, we want to make sure that we are reducing our direct emissions from things like burning fossil fuels on site for, say, a water heater or furnace, and our indirect emissions, that's upstream emissions from the electricity grid. And we can think about when the electricity grid is more carbon intensive, those upstream emissions matter more, or the electricity use associated with them matters more in terms of upstream carbon emissions. So peak hours tend to be dirtier hours, not always, but that's often the case. So the direct, like, it's pretty straightforward. Instead of burning gas to heat water, we use a heat pump water heater, or etc. And then we've got these kind of carbon arbitrage. Arbitrage is like buy low, sell high. Carbon arbitrage might be charge low, discharge high, or shift usage off that high carbon time. So we got a couple questions, like if decarb is a major value stream, okay, where's the carbon coming from, right? You rob banks because that's where the money is, right? That was what was it John Dillinger, I think, said in the 20s. So find where the carbon's coming from. Is it mostly on-site? Is it mostly electricity from off-site? Then we dive into that. Okay, what can we do about the big ones? And when we're talking about electric, when is the grid high carbon and when is it low carbon? In terms of resiliency, that's very often the first place people go, or maybe it's most often the second place. I like to think about passive survivability. People think they want a resilient building. Batteries come to mind, but maybe we don't need that critically. Maybe what they really want is a building that stays habitable for 1 to 5 X number of days in some condition or another. And passive survivability can help get us there. So even having that metric as something that people are thinking about makes a difference. And then, of course, on-site backup energy resources. And some of these facilities are public facilities, like school or a community center. Are they trying to provide resiliency beyond the building? So helping people think about how many hours of passive survivability do we want to have? What conditions are those in? Is that summer? Is that winter? Can we island from the grid? Is it possible to turn off grid power and use our own internal resources? And what stays on in those modes? Cost savings is probably the number one that people care about the most, not surprising. And so we want to think about what's driving costs. There's upfront costs and there's utility bill costs. Ongoing costs are, utility bills are a good chunk of ongoing costs in many cases, and demand charges are often a good chunk, like maybe a third of utility bills in a decent number of commercial buildings and larger institutional buildings. Demand charges are basically the price you pay for the peak kilowatts that flow through the meter over some 15-minute period. Wherever the highest point in time, you're like, hey, 72 kilowatts flowed through. Cool, you're going to pay for those 72. If you can drop it, you save money. And then we're seeing more time of use rates where the cost of energy is higher during peak times, like say in the summer from 5 to 9 p.m. might cost more than the rest of the time. And if you can play nice with that, use a little less energy when it's expensive, you save money. Then we of course have direct payments, like participating in a demand response program, where you get an automated signal, you use less juice during that time, and you get a payout. Those are present in both PGE and Pacificor territories. So we want to ask, what's driving the peak load in each season? Sometimes we have a summer and a winter peak. Especially in the Northwest, it's pretty common to be dual peaking. What are the savings that come from that? What kind of incentives can we pull? And are there any regulatory sticks as well as incentive carrots that are present? Okay, those are the big four. I don't want to ignore that there are equity considerations to be kept in mind here, especially in multifamily buildings. The question of who's on the hook for energy bills can matter, and that gets into the split incentive question, where maybe the building owner pays for capital costs, but the renters are on the hook for operational cost. So we got to think about what the design decisions mean for people in the building, and what resiliency decisions mean for the people in the building as well. Plus, if we're expecting occupants to do something, we have to make sure, like, can they really do it? We were working with one project looking at retrofitting smart grid controls on an affordable multifamily building. This is outside of Oregon. We ran into roadblocks because the thermostat signals were sent in English, and most people in that building didn't speak English. So that, you've gotta make sure it's actually going to work in the real world. Okay, so that's kind of the why, right? Resiliency, cost savings, greenhouse gas savings or environmental protection, and maybe some regulatory stuff in there kind of upcoming a little more. Let's get into what happens in the building. So I'm gonna like bang on this so many times with a hammer. Efficient, flexible, controllable. Those are the three things, right? Passive first, high efficiency, and off we go. I'm gonna give a little bit of sort of specifications at a glance here. So to make buildings be efficient and flexible, we wanna make sure we reduce the peak demand and be able to shed or modify load. So on the right, those are some graphics from the US Department of Energy, talking about how these different types of interactions behind the meter in a building can change the load shape. These can be scheduled. These can be, first of all, passive, like envelope and air sealing. That's just always there. You don't have to do anything. It's not even on. It's always there. They can be scheduled. The schedule happens every day, day in, day out. They could also be based on a smart signal, like a demand response program or a greenhouse gas intensity signal. And then we want systems to be future-proofed, if you like, to be controllable and connected. That means take a signal and do something with it. So be able to receive a signal from the grid, like something over, say, an OpenADR network. There's those standard communications protocols. OpenADR is the standard for many smart systems by which they can, we know they'll be able to talk to the grid, and a lot of utility demand response programs lean on that as the language. But not all. Water heaters often use CTA 2045, also called the EcoPort, which is sort of like a smart plug, kind of like a USB plug, but not the same thing, for water heaters to take a signal and do something with it. And this can be whole building. This can be at the device level, where you might have like a lot of different water heaters, or it can have some other aggregation approach. But it's usually one of those two, and most often these days, it's device level, where there's an aggregated mass of thermostats or water heaters, or EV chargers. So we want to make sure we're interoperable. That's where standards like OpenADR 2.0b or 3 come in. Right? Can we spec things that are interoperable? This system talks to that system. The BMS can control the lighting and the HVAC and the water heating, and it can talk to the grid. That's where we really like to have these open standards, and make sure that we can do stuff automatically and the people stay happy, occupant comfort. Naomi showed this graphic earlier, so I won't go into depth, but this is kind of some of the stuff that we're talking about. And I want to be sure we're clear as we're talking about modeling. Some of this is stuff that's just always in the model, like the massing and the orientation and the fenestration. Of course it's in the model. That's what the model's made of. Some of this stuff is maybe not exactly in the model, but it could be, like a controllable heat pump water heater. The controllability comes in maybe fiddling with the schedule. Well, if we controlled it this way and reduced power from 5 to 9 in the summer, here's a new schedule for the water heater. And some of it is not really in the model, but post-processed, like solar panels or battery energy storage systems. Those often come in later, and we've got some cool tools to do that. When we're talking about speccing out the building systems, the very first thing is, hey, customer, why do you care? What's your value streams you're trying to get out of this? And then we want to take that to sort of a whole building approach where we're thinking about the whole building as a system. And we're able to keep in mind that efficiency and flexibility have connections between them. One way I think about that sometimes is say that energy efficiency can be an impact multiplier for demand flexibility. If your envelope is better air sealed and better insulated, when you turn down the thermostat, you can coast for longer. So that's kind of what I mean by taking an integrated and whole building approach. We're thinking about the implications of these all in one go. Modeling is kind of the best way to do that. And so we're gonna go through system level by system level. Hey, here are some key specs for this system. But I just want to keep in mind that the purpose of going system level by system level is so that they can go into the model and we can take this overall picture that allows, in the end, it allows us to strike a balance, say, between efficiency on the envelope and efficiency on the HVAC system, or energy efficiency in general and battery. Maybe we can get the same resiliency goals through a different balance of investment in envelope efficiency or battery capacity and size. So we're starting with why. What are we doing here? Resilience. There's some key questions that we ask. I had another meeting recently where the client said, okay, so our resilience goal is to stay online for 7 days. Okay, which 7 days? Well, we're not sure. Cool, summer, winter, probably both. Okay, what is staying online during those 7 days? Well, that's a good question too. So we quickly get into the conversation of what are the loads that are staying online during which season, for how long, and what's powering that. In that case, they wanted 1 day on battery and the rest of the week on generators. That eventually, once we kind of chew on this a little bit, that gives us sizing considerations that go into the modeling. Same kind of questions can apply, or similar questions can apply on cost savings. What's our budget? What's our budget for the different components of the building? What are our targets on cost? What are operating cost targets? What are capital cost targets? Similarly, greenhouse gas emissions. Have we defined a greenhouse gas target for this building? Is there only an EUI target, an energy use intensity target? Can we translate that to greenhouse gas? And what are we measuring this against? All in all, it's really key to be able to compare this stuff apples to apples, and often putting a dollar value on the resilience and the emissions can help us kind of bring those to a consistent net present value of the lifetime impact of upfront cost, operating cost over the life of the building, greenhouse gas emissions, resilience, potential downtime is what I mean by that, right? Like put a dollar value on it, bring it all back to today, and we can compare, we can make really well-informed decisions. The modeling is a big part of what helps us get there. And I kind of covered this big picture trade-offs considerations, right? Like that's what I mean, the impact multiplier for demand, for demand flexibility, right? Investment in air sealing and insulation. That may not only mean we don't have to buy as big of an HVAC system, it may also mean when we try to go flex it, we get more out of that flex. Also, risk mitigation really resonates with some clients. So when we come out the other end of the modeling, we can talk about things in terms of risk mitigation. All right, let's get a little more specific. Not every building has big, complicated everything with a fancy building automation system. Plenty of buildings have standalone systems, rooftop units, unitary water heaters, lights that are run mostly with switches and in-place occupancy controllers, not central controllers. That's fine. We can still look at that in terms of future readiness. Those communicate, we can have smart onboard communications per unit, a smart thermostat, a water heater that has a CTA 2045. And we can think about optimizing those systems, system by system. We still want to have a holistic view, but it's not like everything has to be a big fancy integrated BAS oriented building to do this stuff. In general, the modeling considerations, we're often talking about iterative or parametric energy modeling, where You do a model, you mess with it, you do a model, you adjust some things, you do it again, and we see what we got, what came out better piece by piece. There's a couple of key metrics that it's helpful to think about when we're dealing with iterative energy modeling. In the case of future-ready building priorities, sometimes we like to look at the peak watts per square foot demand through the net demand through the meter on the design day in the winter and the summer. So we say, here's how much power flows through the meter on design day at design peak hour, like 3 p.m. or whatever. Okay, cool. Based on our parametric energy modeling, how much can we trim that? How much of that is permanent or passive shed, and how much of that is flexible shed? So we want to start in the baseline model looking at what are the end uses that drive the design day peak power, and then we know where to start looking for savings opportunities that we want to parametrically model. Best if they align with high net load hours. Those tend to be high cost and high carbon. That might be peak time when we're at a time of use rate that's higher, or that might be times when the grid is particularly high carbon. They're often, but not always the same. Summer afternoons, like, is the first kind of place to look. Weekday summer afternoons, 5 to 9. And then we want to, sometimes it's really helpful, like this stuff can be full of little rabbit holes to go down. So it's nice to find simple, consistent frameworks. I was working with a client in Southern California that said, we're going to put in a solar and a battery system. Well, anyway, we're going to be ready to put in our solar and battery system. We're not going to do it yet, but we want to design all our stuff, the conduit, the roof space, the mechanical room, so that we can put this thing in. And then we came up with a pretty simple goal. They wanted to be able to, by the time they installed it all, to have zero net load coming through the meter from the utility during summer peak design day between 3 p.m. and 8 p.m. So they wanted to be sort of invisible to the grid for those 5 hours. That's a pretty comprehensible single sentence that we all got on board with. We all decided that's a good idea. That went into the owner's project requirement, but it also was really helpful in terms of sizing, because that tells us how much capacity we want in the battery, the solar, et cetera. So if we can find some kind of like a straightforward design goal, that helps define a lot of other pieces. And that may be designed in terms of cost, resiliency, emissions, right? Those key value streams. Okay, let's go sort of system by system. I'm going to give a couple specs, and then Forrest's going to talk a little bit about some key modeling considerations when you're actually building a model. We start with envelope because passive first. So I recommend following the Advanced Energy Design Guides or other code standards. Passive House is obviously the most gold standard, to make sure that we're specifying an envelope that is beyond code. And we want to prioritize strategies that reduce coincident peak demand, which is to say peak demand during times that really matter, like high cost, high carbon times, summer afternoon and the coldest times of winter. So air sealing, insulation, orientation and shading, right? How are we orienting this building? Sometimes buildings can self-shade in certain orientations. If they're rotated, maybe one piece of the building shades the other from the southwest or the west face, which is of course when the sun is hottest in the afternoon summer hours. So that helps reduce that peak. And we can start thinking about some of those passive strategies, including building mass. I'll let you take this one, Forrest.
Thanks, Alexi. So yeah, as Alexi mentioned, a lot of the modeling, particularly the envelope modeling, these are things that we're already incorporating into our designs, but it's looking at them a little bit differently within the model. It's looking at specific points in time versus your annual usage, your overall annual energy or energy use intensity. And so some of the strategies that we often look at around envelope may not have a significant impact to that annual energy usage, but they have a more significant impact to some of those peaks. And looking early on at how the orientation may shift that peak and understanding how does that interact with the overall grid peak. So taking a pass and just understanding, okay, I've modeled each of these different orientations. I've looked at the peak that's coming out of that, and then how does that line up with our overall utility peak? Is there a value in one orientation or another? And just understanding how that shape kind of shifts around. Doing a variety of different insulation, air sealing, window specifications to understand, how do those shift the peak? How do they impact the overall peak load, which translates to peak demand? And you'll see, oftentimes when we're doing that, you can tease out the opportunities for cost savings in addition to potential, grid flexibility or demand shedding design strategies. So, glazing tends to be one of the bigger opportunities overall in your envelope, and understanding what different SHGC values versus fixed shading elements may provide for you in terms of that shifting, and also overlaying how that's affecting your overall energy. Oftentimes a fixed shade, while maybe more costly, can provide dual benefit. It can reduce your summer peaks while still allowing some passive solar during your winter, and looking at how that impacts both winter and summer peaks as well as overall energy. And all of this, it's looking at your energy use differently. It's looking at that overall shape of your curve, those hourly outputs that you're always getting, focusing in on those, and it gives the new incentive opportunities give more opportunities for us as analysts to dig in and provide that feedback to owners. So if we go to the next slide, we can talk a little bit about how these overlay into some of the other kind of outcomes that many owners are looking for is within passive survivability. Traditionally, energy modeling does not include outputs specifically around passive survivability. However, it does include the data needed to evaluate passive survivability. The input process is a little bit different for evaluating this, because you want to focus in on specific times within the year, and oftentimes even a different year. Our typical weather file may not be the right weather file to use when evaluating passive survivability. We may want to look at something that shows more of the extremes that we might get in a specific region, understanding if we had a cold snap, a severe cold snap, or a heat dome event, how do those two impact the temperatures differently than our typical year? And it's good to look at both, because it can give feedback on like, well, what's the benefit on your average year? But then if we have this extreme event, how are we going to ride that out? So, part of it's understanding what is the modeling setup in that, knowing how to turn everything off, except for occupants, during those peak events, and seeing how the temperatures ride out. Or maybe even occupants are turned off as well. If you're just trying to understand the building's unoccupied, how are temperatures going to maintain in there, and is freeze protection a serious concern, or is less of a concern for the building? So there's an element of understanding, even in the operation of a building that maybe not occupied, this kind of outage event impact to temperatures within the building. There are a number of different protocols that are out there. LEED has an approach to defining specific thresholds for passive survivability. There's others that have similar approaches, but they all get at trying to understand, the duration of time that occupants are going to experience a certain threshold of temperature, whether it's a low threshold or a high threshold, and how that's going to impact human health. And making sure that we're communicating not only what the model says, but the sensitivity of that. And that's where looking at not only the typical year, but also those extreme years is really beneficial in helping give a well-informed understanding of what resilience could mean for the owner in this particular application. Next.
Okay, so for the buildings that do have a building automation system, which is probably a large portion, maybe most, almost certainly most of the ones we're modeling, couple key specs. We want to make sure that BAS is going to be compatible with all the stuff in the building. BACnet helps make sure that happens. That's ASHRAE standard 135. We want to make sure that it's compatible with the utility to be able to do smart grid stuff. A little caveat on that, that's coming. Portland General Electric has been gathering information from the market about what building automation systems are going to be able to do this kind of automated demand response. So that's coming. It's kind of keep your eye on it. It's not the end of the world if a BIS doesn't have that capability today, but I expect it's going to become more important and more standard as we go. But we want to make sure that the BIS can control all the things simultaneously and have some insight into what capacity might be out there. That doesn't necessarily mean every building system has to constantly be reporting back to the building automation system central brain, I have 7 kilowatts. No, it means we have the ability to send a signal to all the major systems, lighting, at least HVAC, water heating, ideally also lighting, and maybe some other stuff too. There might be pumping or other systems to be able to turn things on and off and have an idea what is available. It's nice, certainly, if we have remote operability and if we can layer on cool apps. There's really interesting stuff coming out, including some AI-driven model predictive control and other building automation system improvements, and some of which are built in, some of which are layered on top. So there's some cool stuff coming out there. On the HVAC side, we want to first start with high performance equipment, right? Very first, we started with passive stuff. Now we want to make sure that the active systems are high efficiency. The best way to reduce peak demand is to reduce load during peaks. That's kind of like saying the same thing twice. But one of the major drivers of building load during peaks is HVAC equipment. And so high efficiency heat pump type equipment reduces those kilowatts substantially, and of course is also zero emitting. So I like to start with that as a first point. It doesn't mean we always land there, but we sure want to. And then it would be a missed opportunity to put stuff in that is not smart grid ready. So ideally there's a control in the system. It's either in the BIS or it's right at the system, depending on how this stuff is set up, to be able to take a signal and do something with it. Sometimes that can be an Energy Star connected product. Only some product categories have that. Where we do, it's a really easy thing to point at. Otherwise, we've got things like OpenADR, the IEC, and the IEEE standards that are shown there. An easy way to do that is to check with the utility that in ETO, that's generally either Portland General Electric or PacifiCorp, to say like, hey, do you play the DR game? Let's make sure that our systems can do that. And often that's through thermostats, and they have lists of thermostats that are compatible with the DR program. Those are pretty easy to find. For commercial buildings, just make sure that you're looking at the list for commercial buildings, because the first most obvious place that you often see is actually the residential thermostats. It's not quite the same thing. So that's kind of so the key things on HVAC. It's either at the system, at the BIS, or at the thermostat.
Yeah, so then in terms of how it's incorporated into models and what the actual impact is to demand, or modeled impact is to demand, it's a lot of getting in and adjusting set points during those peak periods. So again, understanding the overall building peak and utility peak, and looking at, okay, during those peak periods, if we shifted our temperature set points at that specific point in time, or during a week of that time, how is that going to impact it? What are the temperatures going to look like in the zones during those times, and how much is it actually going to float? And that's where your passive strategies are going to lend a lot more flexibility. You're going to have a slower drift in temperature, and then understanding how everything is sequenced. A lot of the potential demand shift is going to be dependent on the way your equipment is operating at the different part load curves and how it's sequenced to stage on. So having soft starts on all of your major equipment, So it can have a slow ramp as it comes on, and having them staged to where the equipment's operating at an efficient point on the part load curve so that your overall demand from your equipment is as low as it can be. And that's close integration with the mechanical design and the sequence of operations, and making sure that as you're working out these strategies, you're identifying these opportunities, that they're actually getting incorporated back into the design documents in a way that allows these type of program savings to be realized, or operational savings to be realized by the projects. And again, it's looking at it from a base schedule, but then looking at different ways that you could optimize it using alternate schedules, sensitivity analyses.
On the water heating side, the big first question is, assuming we're dealing with electric water heaters, the big first question is, are they unitary or is it a central system? If we're talking about unitary water heaters, actually, the very first thing, we're talking about electric water heaters, can we reduce that peak kilowatt draw just all the time? And the easiest way to do that is to use a heat pump water heater. They're about 300% efficient, COP of 3-ish, 2 to 4 maybe, and that is just a simply significantly lower contribution to peak demand. They run more hours, but way lower wattage. If we're talking unitary water heaters, it's a pretty simple spec. Let's make sure that it's got the EcoPort. Conveniently, code says do that. So for electric tank water heaters in Oregon, they should have that, just period. If we can, it's great to be able to spec the 2045B level 2 standard, which makes sure that the water heater can do some cool stuff like advanced load up, where they take a signal and preheat the tank a little bit. You can also get there with a larger tank. That's just more thermal energy. A water heater is a thermal battery, period, and a larger tank is a larger thermal battery, or a mixing valve that allows you to heat the water up to, say, 140 degrees, and then you make sure that 140-degree water never gets out into the pipe, so there's no scalding risk. But it's another way to increase the amount of energy stored in the system, just store it hotter.
Yeah, so water heating, as Alexi mentioned, the big opportunity with load shifting with water heating is the amount of thermal storage that you might have. Typically, when we're modeling these, we're doing this outside of the actual energy model itself. Spreadsheet-based models work perfectly well with the non-interactive. The one caveat to that being, if you do have unitized water heaters that are actually in the space, understanding how the impact of those units are pulling heat out of adjacent spaces, and how that may impact temperature. So that would be the one time when you do want to incorporate it in directly. But the optimization is really looking at that balance between the total heating capacity, so the number of heat pumps you have, and how quickly those can heat up the water. That's point one, and then the other point to optimize is the amount of storage you have. And the trade-off with that is ultimately a space trade-off, and you've got your rooftop equipment typically is where you put your condenser units, your compressors, and then your interior space for your storage. And so that balance, if you have a greater amount of capacity, you can heat up faster, and so you have less, your recovery time can be reduced, and you can do a greater amount of shift. If you have a greater amount of storage, you can ride out a longer period of time with a slower recovery, and you have less compressor. So there's a cost trade-off and there's a space trade-off that's kind of optimized there. And that's where most of the evaluation lies there. And it's a simpler kind of strategy to look, because typically a water heating profile is more, a little more predictable than, it's not as temperature dependent as your space demands, your space heating and cooling loads. So there's strategies, and there's a reason why a lot of utilities already have these programs in place, because there are strategies that can be applied across a broad portfolio that are going to give a meaningful shift. And that's why we see this a lot in multifamily programs, and a lot of the modeling is around those your residential loads, multifamily residential loads. And the value of having a central system versus unitized, I would say that more and more we're seeing projects push towards that central approach just because it gives more flexibility. And with that, let Alexi talk the lighting.
Yeah, and I just want to emphasize one thing too, is recirculation can be a really important driver of energy use, especially in heat pump water heating systems. So central heat pump water heating systems that have recirculation, that's a good place to kind of lean in on the design side, but also make sure that that's modeled realistically. So being able to chat with somebody who knows about this stuff, like an engineer who has some idea how central heat pump water heating systems tend to work in the real world, can make sure that model's kind of doing it right.
Yeah, I mean, I guess just to put a finer point on that, typically with these systems, the recirculation is handled with a swing tank, which is electric resistant. So to Alexi's point, in the impact of demand, you're not accounting for that can have overestimate the value of the heat pump and underestimate the potential peak contribution from your domestic water system. And so, knowing how your recirculation loop is, knowing strategies to reduce the load of your recirculation losses through insulation and more optimized recirc loops is really important to capturing the full picture of how your hot water system is impacting your building demand.
Yep. We don't want people to be grumpy when they're expecting a heat pump water heater system that runs in heat pump mode all the time, and then it turns out their recirc system's doing half the work at electric resistance efficiency, which is much lower. When the model didn't predict that, they're grumpy. Okay, on the lighting side, again, the first goal is to minimize the peak kilowatt hours. Lighting is often coincident with grid peak hours, especially in the afternoons, which is often when grid peak hours happen. So, efficiency first, daylight harvesting obviously makes a lot of sense. That's a pretty well-trodden road in energy modeling. And then there's some stuff out there. California actually has code requirements around demand responsive lighting in commercial buildings. But a couple of key things that we recommend is that to have some kind of a central demand response capable lighting controller, again, with those open standard capabilities to make sure it's interoperable and it can take a signal. And we want to, it's really ideal to be able to dim this stuff so that it's not really obvious to the people in the building. We all notice when the lights flicker or dim, so having the ability to slowly make the adjustments. Ideally, it's imperceptible. The power demand is saved. We adjust lighting for a limited time, and then it comes back up. So that's kind of the general best practice that I would recommend on that. In terms of modeling, we're talking about lighting schedules and watts per square foot. We want to make sure that those schedules are realistically aligned with what gets spec'd in the building. Go for it, Forrest.
Disappearing on me. So the lighting controls, it's just understanding what your lighting system's capable of and how much you can actually dim down, like the percentage of your overall lighting load that is going to be tied to this system is a key first part. And then the actual scheduling of it's relatively straightforward. It does have some interactivity with your heating and cooling system. Ultimately, to the better with your cooling system, because as you dim down the lighting system, you're reducing the load to the space. It does add a little bit of heat load to the space during a winter event, but typically your winter peaks are going to be in the either late evening hours or early morning, and so it tends not to be much of a driver. So that interactivity is not necessarily a detriment to you. And there's trade-offs to be had in understanding, what are the active strategies that we have in these lighting controls and dimming down, but then, what is the benefit of having a really well daylit space first and reducing the need for the more active strategies? You're having the daylight sensors in there that automatically dim it down. If you have a really well daylit space, you're going to naturally dim down your lights during those peak events, because that's going to be the time in which you've got a lot of light into the space and won't need to be leveraging your active system. So, looking at those trade-offs is really important.
Thank you. And then I don't want to leave behind plugs and miscellaneous electric loads. We always take an efficiency first approach. One can have some grid connected appliances. It's emerging, and it's been emerging for a while. So I think this is probably not a major focus in general or in modeling, but I will say, broadly speaking, as buildings get more efficient in general, plug loads tend to take up more of the total. And so having just basic efficiency on our plug loads is really important, and modeling them realistically is also important. So having, we don't want to have rose-colored glasses on when we're thinking about how much energy gets used by plug loads in the building. There are some strategies listed here. I've actually seen, for example, that elevator demand response strategy where during a DR event, one of the 3 elevators is on pause. It's not going to be ideal for every case, and it's not a huge contribution, but it's a thing that some people have done. So that exists, but it's not my #1 place to go. I do want to point out the whole point of modeling is that we are able to think about this stuff holistically, right? We're taking a bunch of individual strategies at these system levels, thinking about the stuff we've been talking about, and then bringing it up to the whole building system overall. That helps us think about interactive effects, and Forrest mentioned a little bit of that around lighting and HVAC. So the ability to build these packages out of individual strategies helps us say to our client, or in the end, when we're done with the model, we can say, okay, option A, B, C, and D, these are built out of packages, or package 1, 2, 3, 4, 5. So just a couple of considerations here. I also want to note that bounce back exists if we model a demand response event by adjusting the schedules, say, of HVAC set points. Say it's summer afternoon, we go from 72 to 74 degrees. When the event ends, we may see a bump in consumption of the mechanical system because now it's trying to get back to that 72. And we may be that may drive an increase in demand, and we don't want to set the demand by setting up that bounce back. And it's just something to pay attention to in the model. Are we potentially setting our demand charge through a bounce back effect or through a pre-cooling effect? It may be that if we try to pre-cool the space to 70 before an event, so we can coast for a while before we get up to 74 or whatever, is it okay if we use more power during that time, or is that going to set our monthly demand charge and result in a predicted higher cost? And that may not, what the model predicts might not be quite how it ends up going in the real world. So there's some details to be considered. And if we're fiddling with schedules to model a flexibility event, just want to make sure that things like bounce back or round trip efficiency from recharging batteries or thermal energy storage tanks are realistically modeled. I don't want to leave behind. Oh, sorry.
Got some great questions coming in, so maybe another 5 minutes or so, and then I want to make sure we get to some of them.
Cool. A couple of items on solar PV. Again, we want to make sure we were specifying smart stuff. There are some specs there. And then PV modeling is often done after the energy model. And we want to make sure that we are, when we do that in a post-process way, that we're specifying the solar with some storage if that's realistic, and we're co-optimizing for cost and carbon. And when we're talking about doing it with storage, we want to make sure that the storage systems can, as I like to say, take a signal and do something with it. We've got smart inverters. And then that we are, this is what I was saying, co-optimizing for cost and carbon, that we're thinking about what the system dispatch strategy is that we're modeling. Like I said at the beginning, what is the priority? What circuits are powered? What's the system size, and what's the system size? And how much reserve do we keep? Some demand response programs that call on batteries say, we're going to leave you the last 20% of your battery all the time in case you need it. Sometimes you might set that reserve higher. That impacts the functional size of the system, because if you never want to go below 20, you want to know how much you have in your upper portion. Any other notes on
also
battery?
Understanding the frequency at which you're cycling the batteries is really important. Okay. It can impact the life of the battery and how it's going to operate efficiently. And I can't stress enough the co-optimization of cost and carbon impact, because the signals, while they're often similar, they're not the same. And we have seen in a number of cases that there is a discrepancy. If you're only optimizing for one, you may be negatively impacting the other to some degree. And so, we want to be able to provide the best outcome for our clients, which is an overall net decrease in cost and net decrease in carbon. And there are different ways that can be approached. Unfortunately, there aren't a lot of tools that are like fully baked to develop that. We do have some tools that, if we have time, Noah's going to briefly run through that to start to look at that.
Yes. EV chargers can be a large driver of load. And if you're specifying EV chargers, we want to make sure that they are capable of taking a signal. You can also consider automatic load management systems as a way to charge multiple vehicles at the same time without driving a really high peak kilowatt usage. And that's kind of what's shown here in that little graphic, where we can say, hey, we never want to see more than 60 amps running through these 3 chargers. Here's how that might happen. That's often kind of a post-processed affair, and maybe it makes sense to let Noah run through our really neat little demand analysis calculator tool for a few minutes before we pause for questions.
I'm going to be showing you an intro to this great tool today, developed by the Future Ready Buildings team on behalf of the Energy Trust of Oregon. I'm Noah Gabriel. I'm a project manager for the New Buildings Institute under our Building Innovation team, and I get to work on building out this tool with the goal of helping outreach managers and sustainable building designers kind of understand several key metrics related to building performance. And what you can really do here is just input models, data, basically hourly or 8760 data that you get from any sort of modeling, say your Energy Plus type tools or something similar. You'll be able to take that exported data and model several different scenarios and get key outputs like emissions, demand charges, total energy costs. And the big feature of this tool is it allows you to input several different scenarios, what we're calling kind of case A, case B, case C, where you can go from, say, kind of a baseline building, say you're at code level, and you want to try implementing a few different building strategies under kind of the Future Ready Buildings framework, such as passive energy efficiency, like improving your envelope, or something more active, like moving towards an efficient heat pump or using a heat recovery ventilation system. So we'll go through how this tool works today, go over inputting some example data, and then show you what results you get. So just for some context here, we're going to start on the first tab, which is the introduction tab. This just provides some context and shows you what the different color codes mean. So that doesn't necessarily relate to these bottom tabs, but rather it's going to relate to columns that you'll see later on. So There are some places you're required to put information in, some that are optional, and some that are just calculations. And then you see red here that you might be getting an error bar. And then we also have references and data. So let's first go into our inputs tab here. And this is where, after you do energy modeling, receive an 8760 data output, you'll be able to simply copy and paste in these three blue tabs. As I said, those correspond, and we have a little nice label here. Those mean required, meaning you do have to put something in. So first off, you're going to go and select your electric utility input. So that can be Pacific Power or Portland General Electric. And then if you're a gas utility, you can select Avista, Northwest Natural, or Cascade. We'll very likely add to these options in the future, but for now, this tool is Oregon focused specifically for ETO's territory. So really the only tabs you'll have to paste in here are these three cases I was mentioning. So case A, building demand and gas use, and then same thing for case B. And then case C is optional, right? If you want to try a third scenario. And then also optional is your solar energy production if you do have solar generation on site. That being said, I've already pasted in some example information here. So this is from a real world community center building in Portland, Oregon. There were three different model scenarios. So case A was simply using a code standard ASHRAE 90.1 envelope. So basic envelope, right? Just building the code standard. The case B data example that I'm using here is adding a heat recovery ventilator. And then lastly, going almost towards a passive house US standard level of insulation and air sealing and all of that, basically measured by the number of air recirculations in an hour that is almost at the passive house level standard. So super tight, well insulated envelope for this case C. And as you can see, we don't have any gas in this particular example building. If your building does have natural gas for heating or water heating or some other end use, you can input the same 8760 data here. This just happens to be an all electric building. So you're going to put those things in. Don't actually worry about these over on the side here. These are just being calculated automatically. So yeah, just worry about this for now. And then let me just take you a little bit behind the scenes here before we dive into results. So let's go to data and tables here. And this is what's going to explain really what the calculator is pulling from. As you can see for both Portland Gas and Electric, and then also for Avista and all the other utilities here, we have the price tables baked in so that it's kind of a clear reference for folks to see. If these change, it's pretty easy in the tool to just, change the rate basically. And we have a couple other tabs of note. Again, you don't have to enter anything here, but this particular tab is just for hourly cost calculations. And this tab is kind of showing you greenhouse gas calculation. So if you're interested, you can look under the hood and find any assumptions that we're making in those calculations. Okay, so let's go into the results tab. This is really going to be the most important tab. And let me just walk you through what's happening in each of these based on the three scenarios we just input. So remember, that original one was just code level insulation and envelope. Case B is adding a heat recovery ventilator. And then case C is improving the envelope almost all the way to the passive house standard. So we can see that the maximum peak demand for case A is about 50 kilowatts. It goes up a little bit, understandably, because we're adding a heat recovery ventilator, so that's an additional load for case B. And then it drops again, going to that passive house, near passive house level envelope in case C. And what's nice here in this table is you can see improvements for each one, and it's color coded to kind of make everything easy to read. So we can see, for example, going from case A to case C, we're dropping our maximum peak demand by 6 kilowatts. In the winter, it's even more kind of staggering here, right? We're seeing a, anywhere from 17 to 23 kilowatt improvement. And so it's just a really easy way to basically say, hey, am I dropping my peaks? We also look at coincident peak, and all that means is it's the building's peak if that's happening at the same time as the entire grid's peak, which is usually in the late afternoon during the summer, and both the morning and the late afternoon in the winter. This table also gives a bunch of metrics related to cost. So we can see here that electricity costs are actually super low. That's because we have solar built in, and I'll show you what this looks like in a moment if we take solar out. And then demand charges are a much larger part of the picture here, because even with solar, we still have times where solar isn't being produced, and therefore quite a large demand charge. As expected, no gas costs, because we don't have that in this scenario. And then you can also see your annual energy costs, which is just summing gas plus electricity. So no emissions from gas here, but then the table also shows your GHG emissions in metric tons for a couple of different scenarios. And you can see the massive improvement from case A to case C just by really improving that envelope. And then in the results here, we also get two pretty important charts. So the first one is going to be your peak day. So this tool is going to automatically find the day with the highest peak load for both the summer and the winter. And then it's going to visualize the load curve for cases A through C. And we can see that it's not super dramatic for this peak day from case A to C, or even A to B in figure 1 for the summer, but that's because Portland is more primarily focused on heating rather than cooling loads. So if we look over here for figure 2, we can see there's a dramatic reduction from over 60 kilowatts for that winter peak down to below 40 for KC. So it gives you a great idea of how much is your building basically being a good grid citizen. Under the hood here again, just you can see how all of these calculations were done. And then this table finds all the peak days. So if you want a clean export version of your hours and your cases A through C and whether or not it was on peak, you can find all that data and do separate analyses this way. So last thing I wanted to show here is just if we change our inputs at all, say we take away solar production, which is easy to do here, our results will update. And as you can see, all of a sudden, it's a major change in, oh, it's just finished uploading. It's quite a change in annual electricity costs. So you can see it went from almost nothing because it's so much solar generation to, the electricity costs almost equaling the demand charges. And then we can see that the peak shapes have changed a bit too, looking pretty different in both the summer and the winter after taking away that solar generation. And you can have that drop in the middle of the day, right, without solar there. So yeah, that's the functionality of this tool. I hope this was helpful for y'all. And if you have any questions, feel free to reach out to the team, and we're happy to walk through more.
That tool is really I'm excited that it's out there. So in conclusion, a little bit, models are the critical step that helps us do these holistic considerations, think about the impacts to the total building outcomes, design outcomes from all these little decisions around insulation levels and HVAC system types and schedules and so forth. And through some of the strategies we talked about today and the ability to take, for example, energy model outputs and throw them into a tool like that, we can start helping people achieve those goals, whatever it is they're here for: lifetime cost savings, greenhouse gas emissions reductions, resilience and passive survivability, et cetera. And really start kind of getting some of that outcome. And some of it can matter a surprisingly large amount, right? National Institute of Building Sciences says resilient buildings construction practices, like in the codes that they're specifically referring to, are like a 10-to-1 savings in terms of eventual savings per investment. So these can be, once you put a dollar value on this stuff, it can be really meaningful. And tools like what we just showed help do that. So some final thoughts. We want to make sure we start by like why are we here? What do we care about? What are the value streams? What are our goals and targets? And then big picture, we want to make sure we are reducing coincident peak demand. We're enhancing flexibility, and we're poised for the future by having stuff that can be smart grid communications ready. We start with passive systems and efficiency first, and we're always trying to get 2 birds or 3 or 4 with 1 stone. So what are the strategies that provide benefits across multiple value streams, resiliency and greenhouse gas savings and cost savings? That helps us decide where we're going to throw those limited dollars. And of course, speaking of limited dollars, right, I just want to harp again, there are dollars available to help do these. There's the early design assistance up to $6,500 toward a charrette. And then there's the more in-depth technical assistance, which can come up to $10,000 to help actually do this energy modeling we're talking about today. So please do avail yourself of those generous incentive levels. It can make a big difference. And Forrest is going to be leading an in-person training. So save the date on Thursday, September 3rd, a lunch meeting in Portland to do kind of the 401 level of this. This has been maybe the 101 or probably 201 level, but Forrest is going to go more in depth. So if this was just a teaser for you, you're in luck, because September is your chance to really get into it.